Hello, this is Module 5, Video 2, continuing on the topic of amines and picking up where we left off with the Manic reaction. So this begins with an amine and attacking a carbonyl group like this as a nucleophile, creating this bond here. Plus and minus charges in the intermediate, but then protonation, deprotonation gets us to here. An amino alcohol, perhaps. Continued protonation creates a great leaving group there, great LG, setting it up for this internal reaction where the lone pair on nitrogen can come in and kick off that great leaving group, and finally getting to an imine, sometimes called iminium ion in the usually older nomenclature. The imine has reactivity very similar to a carbonyl group. Notice it's electronically set up in a similar way. And it wasn't long before an enolate ion could come along. I think people said, hey, we can do carbon nucleophiles like this. That carbon nucleophile attacking what would typically be a carbonyl carbon, but in this case it's an imine carbon, driving electrons toward the plus charge on nitrogen and creating this new carbon-carbon bond. But then you still have the amine present in the product. So the Manic reaction was a great route toward a lot of nitrogen-containing natural products. Often we call those alkaloids. So this is a brief, not showing all the details, synthesis of the alkaloid Retronessine, which is called a Pyrilizidine Alkaloid. And it's from Senecio species of plants, the Senecio genus, I should say. Toxic to livestock. So there's been a lot of alkaloids that are toxic to livestock. And pyrilizidine alkaloids are especially prominent among alkaloids that are toxic in agriculture. These plants kind of grow wild, unexpectedly the cows eat them or the horses eat them and get sick or go nuts. So Retronessine, a pyrilizidine alkaloid, from this starting material, which perhaps was put together prior to this, in several steps, you can create the imine here, right? If you abbreviate that process, you can create that bond there. A couple more steps, you can create the imine. Similar steps to what we just did above. And then the imine can react with this enolate there in an intramolecular reaction, so same kind of thing up here, and that new bond being formed, and the imine, that should have a plus charge there, left that off prior to this, and then you get access to the pyrilizidine ring system. And several more steps, oxidation reduction kind of thing, you get to Retronessine. There's pyrilizidine alkaloids that are well known like this, that are simple like this, but also have others that have been made more complex with additional biosynthetic steps. So what we're seeing here on the left is the biosynthesis, the believed biosynthesis of Retronessine here from putrescine, a simple diamine. The SH is not sulfur and hydrogen, it's an enzyme. And enzymes basically control all these steps. And they also can control the configuration stereochemically. So putrescine is chain extended, 2 units of it, to homospermidine. You can get an iminium ion or imine shortly thereafter, connecting here, right? And then through enzymes, you have ring creation. Note here that you have both configurations, R and S, but actually it doesn't matter because later you take out the stereochemistry there and make an alkene, so in retronessine. So the point of bringing this up is that imines also are used in nature. Even though the whole rest of the process is very different, there's still a key imine step in the biosynthesis. And while we're on the topic, organic lab syntheses that make use of similar steps to biosyntheses are called biomimetic syntheses. Just thought I'd throw that out there. And here we have another example like what I was mentioning earlier, where there's a little more detail and getting to retronessine from these precursor molecules that we already have seen to the left. But then also introduced in what you would call a convergent synthesis. So in other words, a starting material that has been through several steps to get to here, and another starting material from amino acids like L-isoleucine, making another precursor here, and then the synthesis converges. Convergent syntheses are a way to maximize efficiency. For obvious reasons, the opposite of a convergent synthesis is a linear synthesis, where you just continually have to add one block at a time, one piece at a time, in a linear fashion. So this is a convergent biosynthesis. And the other thing we can point out, and so senecionine is sort of the flagship toxin from Senecio species, made from retronessine, we saw earlier, and senesic acid, and in a convergent biosynthesis. So some really interesting stuff in the realm of biosynthesis, and similarities between lab syntheses and biosyntheses in terms of certain intermediates like iminium ions or imines, and also in the concept of convergent biosynthesis.